right? And what is not clear, or what you may not pay attention to before, was in order to define the curvature, you have to define the coordinate system. And what the customary chosen, the reference system is usually like this. The horizontal axis being your x-axis, and the axis pointing downward usually is your y. If you do it this way, then the internal moment has, the positive internal moment has the following definition, which is the one we used before. Which is like this. If that's the case, then we said M internal equals negative EI.
Professor, could you scroll down a little bit?
That's it. I cannot go any further.
Oh, it's getting the image is getting cut off.
I can see it just fine.
Yeah, you have to move the screen on your computer. Can you move it? Move the window.
I'm on a PC. I can't adjust it on that. It's the bottom of the Zoom meeting thing is in the way.
Is that the same problem other people is facing now?
You should be able to like click and drag that those boxes over the videos.
Can you resolve it, Josh?
Yeah, I think so.
All right. Now, where's the clarification? This is just definition. Clarification is this. It's about how we calculate curvature. Example 9 is on your textbook, and I know that some of you have the textbook and others don't have. If you have the textbook, you probably notice that most of the examples I have solved so far, they are from the textbook, and even including this example. This is a cantilever column subjected to 2 axial forces. And you will need this example for your homework, I presume. So far, most of the examples are from the textbook, the chapter of column buckling. So what is this problem? This problem is like this. Suppose we have a column like this, and the total length of this column, I think this is on page 85, if I remember correctly. This is page 85. On textbook. Now the total length of the column is capital L, and at the midspan, which is somewhere here, the column is subjected to an axial force P. So there's a force P acting right here. And at the top of the column, there's also another force, which carries the same magnitude. So also axial force P. And in reality, you wonder how is that possible? Just think about like frame structures, right? The force acting at the midspan could be coming from the floor, such as like this. Suppose you have this, you have dead loads here, and you can pass the dead load to become an axial force acting at like this. So in reality, of course, this would happen especially to building structures. And everything else is the same. That means we have a homogeneous column under consideration. That means we have uniform EI. E and I are both constants. E, I, and our objective is to find the critical level, PCR, of this column. That's our goal. Okay? So let's start solving this problem. First, of course, we've been using the force approach, and let's not make an exception for this one for now. Use bifurcation approach. To do that, you have to establish a free body diagram. And before you create a free body diagram, you have to assume what we call kinematically admissible displacement field. This, you probably heard about this before, but maybe, have you heard about this from structural analysis or mechanics or strength of materials? Well, this is what we call kinematically admissible deformation. Sometimes we call displacement. You can call it field or you can call it profile. What it says is you have to consider that given these boundary conditions, given this type of loading, what will be the possible deformation that this column can exhibit? So that's basically what it says. In this case, we've been using the same concept since the very beginning. In this case, we know that because of the fixed-ended support at the bottom, let's call this point A, and point at midpoint is called point B, the top is called point C. Now, because of point A is a fixed-ended, that means the slope at the point must be 0. The right angle should be preserved. That is what we also, one feature we call kinematically admissible. Because of the fixed-ended support, there cannot be any rotation. And for that reason, the buckling profile will look like this. Right here, it's going to be right angle, right? And then it's going to go up, go a little bit up here, and it's going to go a little bit up like this, something like that. Of course, if we have the numerical, some computer programs, this profile can be made much more realistic than what I'm doing here. Now, by considering the force acting here, another force acting here, be like this. What about our coordinate system? We will define the coordinate system like this. Define this to be y, and this way to be x. So that's our coordinate system, which is important because once we define the coordinate system, that means our positive directions for curvature and for what? For slope are all defined. I just realized that I made a mistake actually previous slide. Has anyone noticed here? The curvature definition, right?
Should the signs be reversed for each graph?
Should be reversed, correct? They should be reversed. Why they should be reversed? So let's start over again, because this is important. You don't have to erase your figures. You just have to make just simple changes. For me, I like to start with everything. This is our x, this is our y. This is positive, obviously, right? And the other one is negative, obviously. To make positive slope, that means you're going to start with a positive. To make positive curvature, you're going to start with a positive slope. That means the increase of this one will only keep going further and further. That means starting from this point, it's going to go further and further and further. That is positive curvature. Why? That means the change of slope is positive. So that's why this should be positive. Sorry about the one I made before. And to project it to our problem here, that means to have this kind of curvature, we are looking at the structure like this. That means this is positive. And the same argument applies to the negative curvature. To achieve negative curvature, you start with negative slope and you start reducing the slope or increasing the negativity of the slope. That means from this point it goes further, going further down like this, right? And then that will give you negative curvature. So in this case, y double prime is less than 0. In this case, y double prime is greater than 0. For the black and white, for the black and the red lines, this one is the first order of derivative is greater than 0, and the other one is for the first order derivative is less than 0. All right, please correct this. And on your note, you just have to flip those signs. So you don't have to redraw everything, but I just like to explain clearly that why I had to make the change. All right, I was moving too fast at the point. I just noticed that. And the same thing, that if you copy this, you can do this flip yourself. And I don't have to repeat that part here. Okay. So let's come back to this problem. Now, we defined profile, and the next thing we do is to cut a free body diagram, create a free body diagram by looking at only a portion of it. And to do that, because we notice that there are two different locations, at point B and point C, you have a concentrated force acting on this column. So we have to cut it into two different parts. That means we need to create two different reference coordinates. One is at point A, which is right here, and the other one should actually start from here. To distinguish the x and y's, we might just call them, one of them to be x1, the other is y1. x1 corresponds to y1, and the other one is called x2, corresponds to y2. Like this. And the first free body diagram we're going to consider is only the section of AB. So this is B, this is C. We will look at only this section, which is only this one. Now, before we continue, of course, what is the reaction at point A?